Hello and welcome to Science Talk. I'm your host, Jim Masso. I want to discuss with you what we see here, a study done by Dr. Andrew Glickson. And the URL, for those interested in looking at this article, global research, one word, globalresearch.ca, and then / beyond climate tipping points, greenhouse gas levels exceed stability limit, Greenland, Antarctic ice sheets, with a hyphen in between each of the words. Hopefully you can pause the video and enlarge this portion of the upper screen here to get the CD URL. And so what he's looking at here is greenhouse gas levels exceed the stability limit of the Greenland Antarctic ice sheets. In other words, they're in danger of collapsing. The pace of global warming has been grossly underestimated. We now know that the warming and the melting is exponentially increasing, not linearly, and at a much higher rate. And so the basis saying atmospheric greenhouse gas level has now exceeded 560 parts per million CO2 equivalent, namely including N2O and methane. This level surpasses the stability threshold of the Greenland and Antarctic ice sheets. So climate change is no longer an appropriate term, more like climate crisis. We've reached a point where we have a crisis, an emergency, but people don't know that. There's a big gap between what's understood about global warming by the scientific community and what is known by the public and policymakers. A quote by Professor James Hansen. Boy, is he ever right. By May 2019, the level of CO2 measured in Mauna Loa, Hawaii, has reached 414.66 ppms. It's now gone higher. I think they've exceeded 415, growing at a rate of about 3.42 ppms per year, well above the highest growth rate recorded in the last 56 million years. The total of CO2, methane, nitric oxide, N2O, expressed as CO2 equivalent, has reached at least 563 parts per million. And that's this table here. So you take the numbers in red, you add them up, and there you have it. Here's your total. So CO2, the rate, CH4, the rate, and then N2O. Notice, though, that, CO2 is increasing 3.42 parts per million per year. CH4, methane, and N2O are given in parts per billion. So that's 3 orders of magnitude difference. So now we have CO2 levels here. And they have different models here that show the projected increase or what the projected levels of CO2 will be. Okay. And this is using IPCC emission scenarios. IPCC tends to underestimate things. But you see this dashed line here? That's about where ice sheets break down. So the current rise of this total greenhouse gas levels to at least 560 ppm CO2e, twice the pre-industrial level 280, implies global warming has potentially reached +2 to +3 C above pre-industrial temperatures. Considering the mitigating albedo reflection effects of atmospheric aerosols, including sulfur dioxide, dust, nitrate, and organic carbon, the mean rise of land temperature exceeds 1.5 C. Again, conservative estimate. So the threshold of collapse of the Greenland ice sheet is estimated in a range of 400 to 560 parts per million CO2 at approximately 2 to 2.5 degrees C above pre-industrial temperatures. So that's the space between the blue dashed line and the blue solid line. So obviously, if you're above the blue dash line, then all bets are off. The thing's probably going to melt fast out from underneath you. It is retarded by hysteresis, where physical property lags behind changes in the effect causing it. There's some studies done looking at the Antarctic ice hysteresis. Another way of looking at this is, in addition to this lag effect, is that if you look at the temperature increase from pre-industrial evolution to now, and you look at how much ice that temperature increase has caused to melt, if we were able to cool the planet back down to those pre-industrial revolution levels, not all of what was melted will refreeze. That difference, and another part of the lag, is also another application of the hysteresis concept. And the thing is, the greater the warming is, the greater that difference is from pre-industrial to wherever the warming level is, the more difficult it would be to refreeze. And you get to the point where when you reach about 9, 10, 11 C above pre-industrial levels, and almost all the ice in Antarctica has melted away. So that's another aspect to the hysteresis concept. Threshold for the breakdown of the West Antarctic ice sheet is similar. Greenhouse gas level and temperature condition which the East Antarctic ice sheet formed about 34 million years ago, estimated as 800 to 2,000 ppm at 4 to 6 degrees C above pre-industrial values. So some models have indicated that the warming could reach 7 to 9 C by 2100, which is above this range here, with appropriately high levels of CO2, definitely at least in the 1,000 ppm realm. The cumulative contribution to sea level rise from Antarctic ice melt was 14 plus or minus 2 millimeters since 1979. This includes 6.9 plus or minus 0.6 millimeters from West Antarctica, 4.4 plus or minus 0.9 from East Antarctica, 2.5 plus or minus 0.4 from the Antarctic Peninsula, and citing the work of Renault et al. Based on the above, the current CO2 equivalent level of at least 560 closely correlates with the temperature peak at about 16 million years ago, when the Greenland ice sheet did not exist, and large variations affected the Antarctic ice sheet. That's based on a paper from Gasson et al. In 2016. So let's look at this figure. This is an updated Cenozoic PCO2 and stacked deep sea benthic foraminifera oxygen isotope curve for 0 to 65 million years ago. So keep in mind now, on the left-hand side, where the cursor is now, that's present day. So as we move along the x-axis or the horizontal axis, we're going further back in time. So here's the Cretaceous. So I don't know if I can enlarge this. Let me see if I can enlarge this here. Doesn't really do much good. Okay. Let's go back to here. So what we see right here, this is the Del 18 oxygen. Right? So this is showing isotope here. So when you started about 40 million years or so ago, this is when the ice sheet started to form in Antarctica. And this would be for Greenland. Okay. And then you have the sea ice here. We got seasonal, not sure what's going on here during the Oligocene, and so on. So what this is showing is that the Del levels increase as we go basically to kind of 50 million years ago to the Eocene. And this here is the atmospheric CO2 concentration. And again, we see a spike in the 50 to 60 million. It drops down and then it increases. Well, spike here, it dropped down, increases. This right here correlates to the PETM, the Paleocene-Eocene thermal maximum, when planet Earth had the hottest temperatures that we have data for, sometimes referred to as hothouse Earth. So now, if you look at the scale here, we see that the scale is getting larger as we go down. So what does this mean? Okay, I did a lengthy video called Isotopic Fractionation where I explain all of that. I suggest you check it out. But here's the idea of it. You have isotopes of oxygen, O16, O18, two most common types. To form an ice sheet, okay, you take water from the ocean and you put it on the land as snow, which then compacts into ice. Because O18 is heavier, it is more likely to stay behind in the ocean, less likely to become part of the snow and ice on land. So what happens is that the ratio of O18 to O16 increases in the water. We see the signal in organisms that take in oxygen to make their tests and shells. So when we have a high oxygen 18 to oxygen 16 fractionation, we know we have an ice age. Conversely, if the O18 O16 ratio is high in the ocean, it's going to be low on the ice. And when the ice melts and starts filling up the ocean, it dilutes the O18, so that ratio drops, right? That's what we're seeing happening here. This ratio is dropping. It's presented as a fractionation, but it is dropping. So here we have, right, we just came out of an ice age. We have the highest O18, O16 in the oceanic cores, but the lowest in the ice cores, and it's the reverse here, if there are any ice at all. So we see this here. When there's no ice age, no ice sheets, the O18, O16 ratio is reduced. You start pulling the O16 out of the water to make the snow and ice sheet, and then you increase the amount of 18 relative to the amount of 16. And we also see corresponding increased levels of CO2. So this is the PETM right here. As the glacial sheets disintegrate, cold ice melt water flowing into the ocean, ensue large cold water pools, a pattern recorded through the glacial interglacial cycles of the last 450,000 years, manifested by the growth of cold regions in the North Atlantic Ocean, south of Greenland, and the Southern Ocean fringing Antarctica, figures 3 and 4. So namely, right there and right there. That's what they're talking about. And then figure 4 here and here. Warming of the Arctic is driven by ice water albedo flip, where dark seawater absorbs solar energy, alternating with the high albedo ice and snow, and by the weakening of the polar boundary and jet stream. I have discussed this many times, that with the reduction in albedo, we're seeing more meridional flows in the jet stream as opposed to zonal, and as well as the gradient not as strong, a bit weaker. So the polar vortex dips down and the jet stream moves a little slower, etc. Penetration of Arctic-derived cold air masses through the weakened boundary results in extreme weather events in North America, Europe, and Northern Asia. Because dipping down, bringing kind of the cooler stuff with it. Warming of 3 to 4 C above pre-industrial levels, leading to enhanced ice sheet melt, would raise sea levels by at least 2 to 5 meters, at least, toward the end of the century, likely 25 meters in the longer term. If you were to melt all of Greenland and all of Antarctica, You would raise sea levels by somewhere anywhere from 67 to 75, 78 meters. And that might take, say, 100,000 years or so, maybe less. Depending on amplifying feedback, prolonged Greenland Antarctic melting and a consequent freeze event may ensue, lasting perhaps as long as 2 to 3 centuries. So it's going to be an oscillatory situation, is what he is suggesting here. 21st to 23rd centuries uncharted climate territory. Modeling of climate trends for 2100 to 2300 by the IPCC AR5 synthesis report in 2014 portrays predominantly linear models of greenhouse gas rise, global temperatures, sea levels. Wrong. We now know it's exponential increases. Therefore, the increase in temperatures, the increase in melting, increase in sea level that they estimate are going to be extremely underestimations. Extreme underestimation. So it's wrong. We now know it's increasing exponentially. So some of what they looked at, the albedo flip, what I just described, okay, so which increases the water surface area and sequestration of CO2, estimates a rise in radiative forcing due to removal of Arctic summer sea ice at 0.7 watts per square meter, a value close to the total of methane released in 1750. Reduce ocean CO2 intake due to lesser solubility of the gas with higher temperatures. Now, if you do introduce cold water into the surface, colder water will be able to absorb more CO2. So that's part of that back and forth oscillatory situation he was alluding to earlier. Vegetation desiccation loss in some regions. Dry areas get drier, wet areas get wetter, right? Reduce evaporation, which reduce evaporative cooling effects. Or increase precipitation, increase wetness in other areas. So you get differential feedbacks from the vegetation. Increase in wildfires that release greenhouse gases. Release of methane from the permafrost, bogs, sediments, fracking, rice paddies. Linear temperature models do not appear to take into account the effects on the oceans of ice melt water derived from large ice sheets, including the possibility of a major stadial event such as already started in oceanic tracts fringing Greenland and Antarctica. In the shorter term, sea level rises, including the Greenland ice sheet, 6 to 7 meter level rise, and West Antarctic ice sheet melt, 4.8 meter sea level rise, referring to major past stadial events, including the 8,200 years old Laurentian melt event and the 12.7 to 11.9 thousand years younger Dryas event. Prolonged breakdown of parts of the Antarctic ice sheet could result in major sea level rise, extensive cooling of northern and southern latitudes parallel with warming of tropical and mid latitudes. And that's according to a report by Hansen. The clashes between polar-derived cold weather fronts and tropical air masses will bound to lead to extreme weather events. Going back and forth, it's a battle here, but the overall thing is that overall the planet will still be warming. So at some point the warming will eventually probably win out. So summary conclusions here. Global greenhouse gases have reached a level exceeding the stability threshold of the Greenland Antarctic ice sheet, melting at an accelerated rate. The current growth rate of atmospheric greenhouse gas of 3.42 ppm CO2 per year is the fastest recorded for the last 55 million years. And it's going to get faster. Allowing for the transient albedo enhancing effects of sulfur dioxide and other aerosols, mean global temperature has reached about 2 degrees C above pre-industrial temperatures. So the notion of keeping it below 1.5, as according to the Paris Accord, good luck. Due to hysteresis, the large ice sheets outlast their melting temperatures. Cold ice melt water flowing from the ice sheets at an accelerated rate will reduce the temperature of large ocean tracts in the North Atlantic and circum-Antarctic, Strong temperature contrast between cold polar-derived air and water masses and tropical air and water masses ensuing in extreme weather events would result in extreme weather resulting in extreme weather events, which retards agriculture in large parts of the world. Humans will survive in relatively favorable parts of Earth, such as subpolar regions, sheltered mountain valleys, where hunting of surviving fauna may be possible. But you ain't going to have no 8 billion people running around. In the wake of partial melting of the large ice sheets, the Earth climate would shift to polarized conditions, including reduced polar ice sheets in tropical to supertropical regions, such as existed in the Miocene 5.3 to 23 million years ago. Current greenhouse gas forcing and global mean temperature are approaching Miocene optimum-like composition, aside from the hysteresis effect of reduced ice sheets. Strong temperature polarities are suggested by the contrast between reduced Antarctic ice sheet and supertropical conditions in low to mid latitudes. Land areas would be markedly reduced due to sea level rise of approximately 40 plus or minus 15 meters, another underestimation. So what we're looking at here in this diagram is you have atmosphere CO2, you have global mean temperature. You can see very nice correlation.
Very clear. Higher CO2 levels, higher temperatures. Lower CO2 levels, lower temperatures. Very straightforward, very clearly seen. We have the evidence for this.
That's shown in this graph here. Oh, okay. How can we sum this up here? Well, first of all, the IPCC once again is underestimating things. They're making the erroneous assumption of assuming a linear increase when it's exponential. So now the question becomes, and you've heard me make this argument, that if you melt enough of the Greenland ice, you can shut down AMOC, and you can tip things into a cooler realm. That's kind of what they were saying here earlier, because if AMOC slows down, and we are seeing the slowdown in AMOC, the Gulf Stream is going to slow down. Well, the Gulf Stream brings its warmth, gives it off, and that's why Scandinavia and the UK are warmer than they should be for their latitudes. That's going to stop. That's going to change. So you're going to see a market change between a polar region and lower latitudes. Right now, the gradient is blurred. So there isn't much of a temperature between. But as this melting continues and you add all that cold water to the surface, at first it's going to create this market difference, and that's going to affect weather. What happens after that is, as the permafrost continues to thaw and add more CO2, now you're going to start heating up that surface water. Not to mention, you're also stratifying the ocean so that you're going to affect productivity, and that could lead to mass extinction. But you're going to start heating up that ocean surface, those upper layers that now have the cold meltwater, that's going to warm up. And that's going to take, this is how I interpret things, that is going to take us into the possibility of another hothouse Earth, as we saw during the PETM. So there will be a bit of a struggle, a bit of a wrestling match.
Because, as Wally Broker demonstrated, when you place cold water into the surface of the North Atlantic, AMOC can slow down or shut down completely.
The planet cools down. That's what the reference to the little Dryas, for example. He showed that. And then as the temperature equilibrate, the upper surface waters warm up a bit. You can then maybe start reforming the ice sheet. You can reinitiate the thermohaline flow, get the conveyor belt going again, and then you start coming out of the cooler temperature regime. So this is going to be an ongoing battle. But if you now have this massive melting, where you increase the sea level by, say, 50 to 70 meters plus or minus, you're going to have a lot less land and have a lot more water absorbing sun energy. That sun energy is going to be given off. And when you start getting to, when you have melting of this level, we're going to create kind of with like a water planet, water world, but you're then going to start getting us to a hothouse Earth scenario. That's how I see this happening. Now, yes, I have made the argument that melting Greenland will bring us into an ice age. But that was before, but I made that assumption based on not all of Antarctica melts. Some of it, but not all of it. If we see the 7 to 9 tenths, even 11C increase, as some models are showing, all of Antarctica ice melts. So yeah, you're going to have sea level rise, 70 meters or so. That's about 210 feet. And that is going to lead to the struggle between the cold, you're going to have a sharp, contrast between very cold oceanic polar waters because of the melt water being introduced and a very hot tropical waters. But water is there's eventually going to be diffusion, temperature is going to mix, that kind of stuff. The water in the tropics is going to continue to absorb sun energy, as will the Arctic in the summer months continue to absorb sun energy, that eventually all the oceans are going to increase their warmth, and specific heat of water going to lead to a hothouse Earth. So there you have it. And instead, some of my critiques include, the IPCC always assuming linear when that's not correct. Stay tuned. Thank you for your time. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.